So now let's get into the math to try to figure out why these certain colors appear on an oil film floating on top of water. Okay, what you notice here, we have different colors of the rainbow, but you also have this white section. In this white section, that film must be incredibly thick, really, really thick, such that, constructive interference is going to happen regardless of whatever wavelength goes in there. But these sections here have very, very specific thicknesses that select only certain wavelengths of light that would match when they get reflected and when they get refracted and overlap. Only that thickness is going to match for that wavelength of light. Okay, so a very important term to understand is that ray number 1 is my reflected ray. Ray number 2 refracts into that thin film medium and then reflects off the next boundary and comes back out and overlaps. And what's going to happen is I'm going to have a situation where these two waves are going to superimpose. And I need to understand, did the second ray, because of the path length difference, which is written over here, did that second ray travel a perfect number of wavelengths to come out and overlap with ray number 1? Okay. And another thing to understand is when it overlaps, are they going to be in phase? Okay, in this case, these two rays are exactly the same, so there is no phase difference, zero radians difference, so they would constructively interfere. On the other hand, if the phase difference between ray 1 and ray 2 is half a wavelength, or pi, they would destructively interfere. So that's the logic here. We're trying to see how many extra number of wavelengths did ray number 2 travel in the oil? And we need to be able to calculate that, okay? And then we have to understand the conditions. How many wavelengths does it need to travel in that oil and come out so that it overlaps with ray number 1? That's the big idea. We are trying to figure out how many extra wavelengths did ray number 2 travel in that oil. And that's going to depend on the thickness, okay, which is my path length difference. And it's also going to depend on something called my refractive index, which we're going to learn about in a second. You've done refraction, so you know what refractive index is. But how does refractive index affect the number of wavelengths of that ray when it goes to the medium? And the last thing that we need to understand is when light reflects, does it undergo a phase change? Okay, and those are the three things that we're looking at. So these conditions allow me to predict how many wavelengths does that extra path have to have in order for it to overlap constructively. All right, so let's get going. In order to get going, let's first review what happens when waves reflect from a boundary. So let's just talk about wave number 1 right now. What happens when it reflects off of a boundary? Okay, so the first thing when we talked about reflection, we talked about ropes hitting a wall. Okay, so if this is a wall and I have a rope that I send a wave pulse down, when that wave pulse hits the wall, it comes back, it flips when it hits the wall, okay, if you remember that. And that was when I introduced phase shift due to reflection. Okay, well, that phase shift happened when that rope hits a wall. On the other hand, if that rope is not attached to the wall, the rope is loose, okay, it's free to move on that wall, what'll end up happening, I'm going to draw what would happen there. If it was loose, okay, if my wave pulse was coming in and it was loose and it wasn't attached to the wall, when it would reflect without a phase shift. Okay, and that's an important thing to remember. So we're reviewing what happens when waves reflect from boundaries. When waves reflect from boundaries, they can either undergo a phase shift, okay, if they're hitting a very dense medium, okay, so if I erased that and I said that it's actually attached to the wall, okay, when that wave pulse would hit the wall, it would reflect with a phase shift. On the other hand, if the wave is coming into a very loose boundary, it would reflect without a phase shift. Okay, so the first question that we have to ask when we look at a reflected ray is there a phase shift. Okay, so if I looked at ray number 1 coming in, I need to ask myself, does that light, when it reflects, undergo a phase shift? Okay, let's imagine the light enters as a trough. So it's entering that boundary as a trough. When that trough reflects, does it remain a trough or does it become a crest? Does it undergo a phase shift? Well, the answer to that is looking at the density of the medium that we're going from. So air is low density and oil is high density or higher density. So let's think about that. If I'm going from low density medium, very free to move, to something that is harder, will it look more like a loose boundary or will it look more like a fixed boundary? Well, the answer is whenever you're going from low to high, it simulates the wall situation. We're hitting something hard. So that reflection would occur with a phase shift. Okay, that reflection would occur with a phase shift. On the other hand, if I'm going from something like this little ray over here, so imagine I'm going up and reflecting there. If I'm going from something that has high density to something that has low density, we can imagine that situation is more like a loose end. I'm going into a medium that's a lot easier, so it's a loose end. So that reflection would occur without a phase shift. Okay, in that case, if a trough entered that boundary here, it would reflect as a trough without a phase shift. Okay, so what do we have? What do we have going over here? Okay, so if I had a phase shift, that tells me that I know exactly what the wave is going to look like when it reflects off of over here. And then at that point here, I know that I would have a crest. Okay, that's going to be a crest. So whatever this is, it also has to be a crest. Okay, so that's an important condition for them to match up. Okay, so now I need to figure out when that wave is refracted and travels through the medium, is it going to undergo enough wavelengths to come out as a crest so that they can constructively interfere? And that's what we're going to talk about next when we think about the ray number 2 for the refracted ray. All right, so for ray number 2, what happens when waves refract into a medium? Okay, so I'm just going to erase the stuff up here. What happens when waves refract into a medium? Well, they change their direction. Okay, we know that. Okay, so, oops. Just going to move that up a little bit. So what happens when waves refract into a medium? We know that they're going to change direction. But not only are they going to change direction, okay, when that ray comes in, it changes its direction. But not only does it change its direction, if I drew the wave fronts, what do you guys remember? What would happen to the spacing of those wave fronts if we went from air to water? Okay, and hopefully you remember that the wave fronts would get closer together. Okay, the frequency stays the same, but the wavelength would shorten. Okay, and the wavelength in, let's say, that medium is going to be the wavelength in medium 1. I'm going to call that medium 2. Okay, this is 2. And that's 1. The wavelength in medium 1 divided by my refractive index. Okay, so the wavelength shortens, and it shortens by the refractive index. So if the refractive index here was 1.0 and the refractive index in water is 1.3, that wavelength was shortened by a factor of 1.3. So let's just imagine that my wavelength was 1 meter. Okay, so if I had a wavelength of 1 meter divided by 1.3 would be the new wavelength. Okay, so it gets shorter. So an important thing to remember is that wavelengths become shorter. That's important. So I need to factor in that when I undergo refraction, the wavelengths are going to become shorter. And that's important because when I'm looking at the thickness, of that material, okay, I need to be able to count the number of wavelengths that go in and come out. Okay, so that I'll be able to predict, is it going to come out as a trough or is it going to come out as a crest? And is it going to overlap with number 1 or number 2? Okay, and that's important for refraction. So in the last video, in the next section, I'll let you guys take a break. But in the next section, we're going to actually come up with the formula to be able to use, to apply, to be able to figure out which wavelength of light is going to be selected based on the thickness of that oil film and the refractive index of that oil film.